Critical temperature and critical pressure. The critical temperature of a substance is the temperature at and above which vapor of the substance cannot be liquefied, no matter how much pressure is applied, while critical pressure of the substance is the pressure required to liquefy a gas at its critical temperature. So, gas can be converted to liquids by compressing the gas at a suitable temperature, and it's become difficult to liquefy as a temperature increase. Okay, from the figure, we can see that the tubes containing water at a several temperature at 25 degree, 100 and 374 degrees Celsius, which is 374 is a critical temperature of the water. So we can see that only water vapor exists in the tube at 374 degrees Celsius. Okay, the other factor that affect the extent of the absorption is the surface area of the absorbance. So when we increase the surface area of the absorbance, there is an increase in the absorption of the gas. This is because when we increase the surface area, there is more number of absorbing sites. So finely divided solid and some porous substance are a good absorbance. And then the third one is the effect of pressure on the absorbed gas. So when the pressure of the gas is increased, the rate of the absorbent increase due to the increase in the number of the molecules striking on the surface. Thus, increase in the pressure will increase the rate of the absorbance linearly. But after some times, it will reach the point when the pressure has no effect on the rate of absorptions, as the number of the absorption site is fixed and no more absorptions can happen in those sites. So the extent of the absorption will be independent of the temperature. Then the effect of temperature on the extent of absorptions. As absorption is accompanied by evaluations of the heat, so according to the Lee-Cattelius principles, the magnitude of the absorption should decrease with the rise in temperature. Okay, the absorption isobar, which is demonstrate the relationship between the extent of the absorptions and the temperature at the constant pressure. A physical absorptions isobar shows degrees in x over m, where m is the mass of the absorbance and x is the absorbance as the temperature increase. While the isobar for the chemical absorptions shows an increase in the beginnings and then decrease as the temperature increase. Absorption isotherms is a curve that expresses the variations in the amount of a gas by the absorbent with pressure at constant pressures. It is a mathematical equation which describes the relationship between the pressure P of the gas absorbed and the extent of the absorption at any fixed temperature. The extent of the absorption is expressed as a mass of the absorbed on 1 unit mass of the absorbance. So, if S gram of an adsorbent is absorbed on m gram of the adsorbents, so the extent of the adsorbent can be expressed as x over m. Currently, absorption's isotherm for the gas piece. In 1909, German scientists provides an empirical relationship between the amount of the gas absorbed by a unit mass of solid adsorbents and a pressure at a particular temperature, and it is expressed using these following equations, which is the adsorbent isotherm is obeyed by the absorptions where the adsorbents form a monomolecular layer on the surface of the adsorbents, which is x over m, which is x is the weight of the gas absorbed by the m gas at the pressure P. So Sm is represented as the amount of gas absorbed by the adsorbent per gram unit mass is equal to constant Kp at a particular temperature and for a particular adsorbance and adsorbed gas, which is n is always greater than 1 and indicating that the amount of the gas absorbed does not increase as rapidly as the pressure. And when it's expressed as a linear equations is equal to log x over m equal to log k plus 1 over n log p. Since the absorption process is exothermic, so the physical absorptions occur readily at low temperature and decrease with increasing temperature, which is based on Lee-Catelier principles. Therefore, porous substances are better absorbents as increase in surface area can promote absorptions and does not require energy for activations. The relationship is generally represented in the form of curve where mass of the gas absorbed per gram of the absorbent is plotted against the pressure. Here the value of n should be always greater than 1 so as to equation be valid for a range of value. This curve indicates at a fixed pressure there is an decrease in the physical absorption with increase in temperature. At higher pressure, the curve approaches to a saturation level and the equation becomes invalid at high pressure. If the pressure is fixed, the temperature and physical absorption are inversely related. Therefore, here the option of concentration gives the combinations of the correct statement. Friendly absorption isotope is not applicable for high pressure, which is at low pressure, which is 1 over n is equal to 1. Hence, x over m is equal to Kp. Therefore, x over m will be proportional to pressure. So, the extent of absorption is varies linearly with the pressure. While at high pressure, which is 1 over n is equal to 0, therefore, x over m will be constant. Then, the extent of absorption become independent with the pressure. While at moderate pressure, which is x over m, is depends upon the pressure raised to the power, which is x over m will proportion to p power 1 over n. The absorption isotopes obtained by plotting the quantity of the adsorbers against the concentrations of the substance in the original gas or solutions at constant temperature. And the Frulich absorption isotopes only valid if we get a straight line with slope is equal to 1 over n and y-axis is equal to log k. Frulich absorption isotopes only approximately explain the behavior of the absorptions and the factor is between 0 to 1. So these equations holds good over a limit range of pressure. The limitations of the Frulich isotopes is it is only applicable with certain limits of pressure and fail at high pressure because beyond that point. And then the value of the constant K and N change with the pressure. In addition to this, Frulich absorption isotope is an empirical one and does not have any theoretical base. Frulich absorption isotope, absorption from the solution phase, which is solid can absorb solids from the solutions. So the following observations have been made in the case of the absorption from the solution phase. First is the extent of the absorption will decrease with increase in the temperature. According to the Lee-Catelier principles, if the temperature is increased, the kinetic energy of the gas molecule is increased and they leave the surface of the adsorbents. Therefore, it will decrease the degree of the rate of the absorptions. While increase with pressure will increase the rate of absorption. It is because when we increase the pressure, gas molecule will be striking on the surface and therefore the pressure, if the pressure is increased, the rate of the absorption will increase linearly. And then the extent of the absorption increase with the increase of the surface area of the adsorbents at a given temperature and pressure. And then the extent of the absorptions is depends on the concentrations of the solutes in solutions and the nature of the adsorbents and the adsorbers. For example, when the solutions of the acetic acid in acetic acid is shaken by charcoals, a part of it can absorb by charcoals and the concentration of the acetic acid decreases in the solutions. Freundlich's absorption isotherm approximately describes the behavior of the absorption from the solutions with a difference instead of the pressure. Then the concentration of the solutions is taken into the account to this equation, which is x over m is equal to kc power 1 over n, which is c is the equilibrium concentrations, which is when the absorption is complete. And then taking logarithms of the above equations and plotting logs x over m's against log c, then we can get a straight line which shows a validity of the Freundlich's absorption isotherm. And using these equations, the validity of the Freundlich absorption isotherm can be established. The Langmuir absorption isotherm derive a simple absorption isotherms on the theoretical considerations based on the kinetic theory of the gases. The isotherm was based on the different assumptions, one of which is that the dynamic equilibrium exists between the absorbed gas molecules and the free gases molecules. Langmuir absorption isotherm depicts the relationship between the number of the active sites of the surface undergoing absorptions, which is extent of the absorptions, and the pressure. According to the Langmuir absorption isotherms, the absorption consists of the two opposing processes, which is condensations and evaporations. The rate of the condensations depends on the uncovered surface of the adsorbents viable for the condensations, which is at the beginning of the process, the whole of the surface is uncovered. Therefore, the rate of the condensations is very high. As the surface is covered more and more, the rates of the condensations will progressively decrease. In contrary, the rate of the evaporations depends on the covered surface. Hence, the rate of the evaporations increases as more and more of the surface is covered. The equilibrium will be set up at the stage when the rate of the condensations equal to the rates of the evaporations, which is called as adsorption equilibriums. The rate of the condensations also depends on the pressure of the gas, since according to the kinetic theory of the gases, the number of the molecules striking per unit area is proportional to the pressure. Therefore, S over m is equal to AP divided by 1 plus BP, which is A and B are constants and their value depends on the nature of the adsorbents, nature of the solid absorbent, and the temperature. Their values can be determined by the experimental data. The Langmuir absorption isotherm is based on the assumptions that the fixed number of Wessons or adsorption sites are available on the surface of the solids, and then all sites are energetically equivalent and the energy of the adsorption is equal for all sites, means that each site can hold maximum 1 gas molecules and the constant amount of heat energy is released during the process. Third one is no or ideal interactions between adsorbed molecule on adjacent sites. The Langmuir absorption isotherm also assumes that the dynamic equilibrium exists between the adsorbed gas molecules and the free gas molecules. For example, the absorption process between A and B, which is A is unabsorbed gas molecules and B is unoccupied metal surface, while A, B is the absorbed gas molecule. Langmuir absorption isotherm also assume that adsorption is monolayer or unilayer. The Langmuir absorption isotherm expresses the relationship between the fractional coverage and the partial pressure of the adsorbents, which is theta is equal to Kp over 1 plus Kp, which is theta is the number of the size of the surface which is covered with the gas molecule. P is the pressure and K is equilibrium constant for distributions of the adsorbents between the surface and the gas phase. The Langmuir absorption isotherms only valid at low pressure and high temperature. It is because the adsorbed gas has to behave ideally in the vapor phase, and these conditions can only be fulfilled at the low pressure. Therefore, this Langmuir equation is only valid under a low pressure. And then the Langmuir equations assume that the absorption is the monolayer, but monolayer formation is possible only under low pressure condition, which is under high pressure. The assumption breakdown as a gas molecule attracts more and more molecules towards each other. So, Bruno, Emmett and Taylor or BET explains more realistic multilayer absorption process. Another assumption was that all the sites on the solid surface are equal in the size and shape and have equal affinity for adsorbed molecule, which is the surface of the solid is homogeneous. But as we know that the real solid surface are heterogeneous. Langmuir absorption also assumes that the molecules do not interact with each other, this is impossible as a weak force of attraction exists between the molecule of the same type. And then the absorbed molecule has to be localized, which is decreased in the randomness as a 0, which is delta S is equal to 0, and this is not possible because on the absorptions liquefaction of gas taking place, which result in decrease in the randomness, but the value is not equal to 0. What will happen to the equilibrium constant at low and high pressure? At low pressure, which is Kp is small, so that the factor of 1 plus Kp can almost be ignored. Kp is smaller than 1, so theta is equal to Kp, or theta is proportional to P. So it will shows the linear variations between the extent of the absorption of gas and pressure. While at high pressure, which is Kp is more than 1, so theta is equal to Kp over Kp equal to 1. So the extent of the absorption theta is independent of the pressure at high pressure conditions. Then the reaction at this stage become zero order.